Testing now.
There we go.
Okay. Hello, everybody. My name is Tony Darnell. I work at the Space Telescope Science Institute. I'm the social media manager here. And this week at the Institute, we have something rather interesting. We're trying kind of a bit of an experiment here because today, tomorrow, and Wednesday, we're having a workshop on the Orion Nebula. And this workshop is designed to kind of present some of the things about the Orion Nebula. What do we know about it? What are some long-standing issues that we're maybe finding more things out about? What are the what's the latest research? What's the new research out there regarding this very famous nebula? If you don't know what the Orion Nebula is, then not only are you in the right place, you're going to find out what that is, but also the cutting-edge research that's being done here. So with me today is my co-host. He's always out here sharing these hangouts with me. Is Scott Lewis from Know the Cosmos. Hi, Scott.
How's it going, Tony? I prefer cohort instead of co-host.
Oh, that's
We get up to some trouble sometimes.
Cohort, yeah. So all right. So cohort. Now I was going to call this a Hubble Hangout, but because this particular topic is more about research done by a lot of other things besides Hubble, kind of, I didn't bring it up this time. But usually we call these under the moniker of Hubble Hangouts. And so with us today are some astronomers attending the workshop, Dr. Massimo Roberto from the Space Telescope Science Institute and Lynn Hildebrandt from Caltech. Hi, guys.
Hello.
Hi.
So Massimo, why don't you start us off by telling us a little bit about this workshop. What are you hoping to accomplish, and why are we doing these kinds of things?
So basically, the story of the workshop starts almost how much? 8 years ago, when we got approved the Hubble Treasury program on the Orion Nebula. We thought years ago that the Orion Nebula needed to be investigated in detail with the Hubble. And the main reason was, at the time, to study, to understand the stellar population of the cluster. You may not know, but the Orion Nebula, which is the spectacular object in the sky that everybody points the telescope in the first night after Christmas, when you buy it, the Orion Nebula is actually host thousands of young stars, of young forming stars. So for astronomers, it's the prototype of star formation. If you want to understand how stars are formed and actually even how planets around stars form, the Orion Nebula is a critical place to go. So we pointed the Hubble. We had this monster program, more than 100 orbits, which means a lot of time. We observed the Orion Nebula with all the imagers on board of the Hubble. At the time was ACS with PIC2 and NICMOS, so in the optical, UV, in the infrared, really the full power of Hubble was spent there. This is the largest program ever dedicated to star formation. And we got the data. One of you may know the spectacular, big red picture of the Orion Nebula is one of the byproducts of this survey. Took some year to put together the data, to clean up the catalog, to write a number of papers. Now everything is basically out, is public. We have released everything to the public. So the idea of the workshop is to bring here the leading experts, those that are working actively on Orion right now, to discuss the status of our understanding, what we have learned from these and other programs that are being carried out, that have been completed, and sort of plan the next steps to share ideas the way science works. We discuss in these hours together new plans. Each one comes with new ideas and new plans. So it's a brainstorming session on the line of the work that has been done in these years with the Hubble.
So is it Hubble centered then? I mean, you said you mentioned a bunch of instruments, which I should clarify what they were. The ACS, the Advanced Camera for Surveys. NICMOS was an older camera that was on Hubble. These are all cameras that you're talking about, imaging cameras, and now we have Wide Field Camera 3, the what I guess they call it WISI 3 around here. So all of these observations, all of the workshops is based around observations done by Hubble?
No, there are of course data taken with many other observatories, telescopes, both from the ground and from space, X-rays, infrared. And especially tomorrow, we will hear a lot about these other observations. On the other hand, let me say that Orion is a region especially good for the Hubble because it's sort of an exception in the field. Normally, when stars form, they are embedded and shrouded in the molecular cloud, in the neutral, dense, obscure material, dark clouds. But in the case of Orion, what happened is that there are giant stars that have blown out the material, so they have made possible for us to see through this cloud. So we see, we basically have a unique opportunity here, well, a rare opportunity to see star formation from an exceptional point of view. Basically, everything has been open to our view, so the Hubble can go through this cluster at optical wavelengths, which is the strength of the telescope. So it's sort of an ideal situation for us to see something extremely young, but already exposed to our view.
Awesome.
So this is why Hubble is central for Orion in particular.
So thank you, Massimo. That was wonderful. So that's the workshop. That's what's going on this week, and this is some of the reasons why they're having it. We're going to get into a little bit more of this later, but before I do, I need to let you guys know how you can interact with us. I forgot to mention that, as I always do. I just want to jump in and start talking about whatever it is the topic is whenever I do these Hangouts. If you want to ask us questions, we would encourage you to do so. You can also leave comments on the YouTube channel, where on Space Telescope or Hubble Site channel's YouTube channel, where I'm looking at the comments from where this video is being streamed. Also the event page, the Google Plus event page, and we are also monitoring Facebook and Twitter as well of the hashtag Hubble Hangouts. So we hope you will give us some questions and leave us some comments, and we'll look forward to getting to some of that stuff a little bit later on. And there's also a little square along the bottom that nobody knows who this guy is. His name is Michael. Hi, Michael.
Hello.
I don't know your last name.
My name's Mike Rector, and I am an amateur astrophotographer. I just set up my telescope with my digital camera and take long exposure pictures to just get nebula and galaxies and star clusters.
So I'm told that those who watch the virtual star parties on a regular basis probably know your name. Is that correct?
Yep, I've been on there a few times.
Yeah, it's one of our contest winners from last May. We had a photo contest of astrophotography, and Mike actually won with the Pleiades.
Yep.
A really great shot.
Yeah, your audio seems a little bit low to me, Scott.
I can turn up my gain. Yeah.
Yeah. Okay.
Is that a little better?
That's much better. Thank you.
I'm normally too loud, so I had to turn it down a little bit.
Tell me about it.
Stop yelling.
All right, so welcome, Michael. In your imaging efforts with your telescope, have you done much with the Orion Nebula?
Yes, I have. I actually sent a picture of Orion to Scott.
So Scott will get that up for us hopefully in a little bit. So that's cool. All right, well, welcome, and so hopefully you'll be able to provide some insight from an amateur perspective, as well as maybe if we have some time toward the end of it, we could talk a little bit about what's involved in astrophotography and how can a beginner get started, because I think the Orion Nebula is probably one of the better targets. So
yeah, there's Mike's Orion right there, which is beautiful. Absolutely gorgeous.
Cow, that's amazing.
It's beautiful. Yep.
That's amazing.
And where are you out of, Mike?
I'm from Plattsburgh, New York, about 40 minutes south of Canada, near Lake Champlain.
Okay. So you have better skies than I do here in Los Angeles.
Yeah.
Just a little bit.
Or better than we have in Baltimore, I'm sure.
Yeah, most likely.
No, that's fantastic.
Okay, so Lynn, I'd like to get you in on this discussion a little bit. So what were your reasons for attending the workshop, and can you tell us a little bit about what some of your interests are, your research interests?
Sure. Orion is just an iconic region, not only for amateurs and astrophotography and the general interest, but also for professional astronomers at a deep level. It has been looked at basically with every new technology we've had for centuries, and the talk I gave this morning at this conference outlined where we've gone basically from drawings in the early days and early years of the telescope right up through photographs, the first photograph that were taken, and on through the decades to our big space telescopes, both at optical wavelengths, the Hubble, infrared wavelengths, the Spitzer space telescope, X-rays with the Chandra space telescope, Herschel, which is a mid-infrared observatory, WISE, also a mid-infrared observatory, as well as a lot of ground-based data at long wavelengths from the millimeter, sub-millimeter, and radio wavelengths. Anywhere, any place in the electromagnetic spectrum that is interesting or is technologically interesting is applicable to Orion. It's just an amazing confluence of the nebula, the stars that are forming, the molecular gas that is there, the planets that are forming there. So my particular interest has mostly been in the stellar population, so trying to understand when we rattle a cloud around, a molecular cloud, what falls out in terms of stellar population. And in Orion...
Can you tell us real briefly what you mean by molecular cloud? We want to... get used to getting interrupted because I do that.
Sure.
Whenever a term or jargon comes out there, I kind of want to help define it before we get.
We have our jargon meter and it starts pinging. We have to really back.
So a molecular cloud. What is that?
You get those PhDs on here, the jargon flies. So in interstellar space, there are particles. There is gas. And there are different densities and temperatures of that gas, and there can be hot gas that is quite diffuse. Molecular clouds are regions of very cold gas, very dense gas, out of which stars are forming or will soon form. And it's, as the name implies, molecular cloud is a cloud cool enough where molecules can survive. So molecular hydrogen, H2 in chemistry format, is the most dominant molecule, but we observe all kinds of molecules: carbon monoxide, methane, all kinds of any combinations of S's and O's and N's and T's. The periodic table, you can combine these into molecules in these dense cold clouds.
So basically, it's a cloud that's cool enough that allows some of these atoms to form molecules. Okay.
Exactly. So when they get too hot, the molecules dissociate. So they become their constituent. H2 molecular hydrogen will become regular H atomic hydrogen.
Is that important in star formation?
Well, it's when an individual star is formed, it's the first thing that happens in these cold molecular clouds is as the what's called a protostar is in the process of collapsing out of the molecular gas and forming, it heats up and starts to dissociate the surrounding molecular gas. And then ionizes it, gets even hotter, removes electrons, and so on in this process of star formation.
So wait, the molecular cloud starts to come together and then heats up as the protostar is formed, and then at some point it turns on. And
correct.
And switches to stripping those molecules apart, as well as even the electrons around the hydrogen, right?
Right. So in particular, in the Orion Nebula, there are some very massive stars. So in excess of a few tens of solar masses, 20, 30, 40 times the mass of the Sun, and these are hot and luminous stars. And so they're putting out a lot of energy, and they are the ones that are in fact responsible for creating this nebula that we see, because the stars themselves are interacting with the interstellar medium and making it light up the way we see it.
Okay, Scott, can you put up that image again from Michael?
Yeah, absolutely. I'm pulling it back up here.
So yeah, let's take a look at that. So this is the quintessential icon we're used to seeing when it comes to the Orion Nebula. And can you describe to us here how first of all there's like there's the big nebula part that I've always looked at where the trapezium is and things like that, and then there's off in the lower right or lower left, I'm sorry, some other clouds and stuff. So how big is this thing?
It's pretty big. So it's
10 parsec?
what is called
10 by 4.
Yeah, it's what's called a giant molecular cloud. So that has a mass of about a few 100,000 times the mass of the sun. And so if you think of turning all of that mass into stars, and if each of the stars had a mass of 1 solar mass, you would make 10 to the 5 stars. You would make a lot of stars, a few 100,000 stars. Now, we don't think that there is a 100% efficiency in converting gas to stars, so the stellar mass is much less. But the entire star-forming region is, about a factor of 40 larger than just that small region that's shown. And so there's a lot of the Orion Nebula is one of the most.
There's a whole lot more we're not even seeing here.
There's a whole lot more that is some of the observatories that have performed all-sky imaging surveys. So 2MASS is one, and WISE is another. These are infrared imaging surveys. You can get a look at the entirety of this Orion region. And in fact, there are many famous pictures from astronomers of the constellation of Orion with various elements of nebulosity throughout it, and all of that is actually part of the same star-forming episode that may have occurred over a few tens of millions of years, whereas the Orion Nebula and other small condensations like it throughout the molecular clouds are star formation events that have occurred in only the past 1 or 2 or 3 million years. But it's just a small but the most dramatic piece of star formation in this entire region.
And also something fascinating is you need a bit of fantasy, but think that in the field of the picture, if you will take the picture from the Orion Nebula in our direction and take a picture of the sun and surrounding, will be basically empty with really a few stars, 10 stars, 20 stars, with nothing, with a lot of empty space. But if we look at the Orion Nebula, the density of stars in that region is amazingly high. At the center, you will have tens of thousands of stars where you would have only one around the sun. In fact, there are not tens of thousands, but 5,000 stars easily are members of the nebula of the star-forming event in the field of the picture. So it's extremely dense, it's extremely rich.
So inside that image that Scott had up before, there's 5,000 stars in that area alone?
At least we know 3,000 in the inner region, and then there is star formation along the filament. Or is a round number because we don't have a complete census, because when these nebula are when they're in the dark regions, we cannot penetrate with our telescope. We need infrared radiation to go in this dark, like the dark filament that you see here now in the center. We need infrared telescopes, and even with the infrared telescopes, it starts to get very hard to look at the very faint sources that are certainly there. But we are talking about, I don't know, 3,000, 4,000, 5,000 stars in this field. I think is a correct number.
Wow, that's amazing. I had no idea there were that many.
Around the sun, in the same volume, you will see, a few.
So so this is glowing, or this nebula is glowing because of those 5,000 some odd stars in there.
No, because of only one.
Only one.
Only one.
Aha!
There is a monster in the middle
that
makes 95% of the glow. There is a monster we call Theta 1 Orionis C, the technical name.
Yeah. So there's only one star that's responsible for all this glowing here.
There is one. There are 5, 6, 7 big stars in comparison to the sun. But one is big among the biggest, and this one makes, I think the last number I heard was 95% of the entire radiation coming from the background, from the nebula, of this diffused blue and red light, is actually reprocessed light, is reflected light from the big one that is there at the center.
Okay. Hey Scott, you were doing something a while ago. I think it was with Stellarium or something like that. What did you have up?
I had a Stellarium up, so I can show.
I wonder if Yeah, if you could put that back up again. And for those of you who don't know where in the sky the Orion Nebula is, Scott's got a picture here of the Orion, the constellation of Orion.
Right.
And the belt are those three stars, those three horizontal stars are the belt of Orion. But hanging down on the sword from Orion's belt is this sort of semi-vertical row. It's more of a cattywampus row, kind of off to the diagonal there.
You should use cattywampus much more. Tony.
Well, it is jargon, but I have to explain that jargon, and so I try to minimize it. So it's kind of cattywampus there, but in that middle area there, it's kind of fuzzy. Now, on a clear, dark night, you can't be in the city, but on a clear, dark night, you can see that with your naked eye. It'll appear basically as a fuzz or a fuzzy patch or a smudge up in the sky. But you can see it, and a pair of binoculars actually bring out some pretty decent detail. So, Massimo and Lynn, can you tell us what the difference is between the Orion Nebula and the Orion Nebula complex? What do they mean when they say that? Or molecular cloud complex, I guess they call it. No.
Okay.
Go in.
So if you zoom in really close on that image or another good one like it, you'll see what are called the trapezium stars, and that's because there are four bright stars in there that are visible in just the smallest telescopes. So that's called the trapezium, and the inner part of this is called the trapezium cluster. If you go out a little bit, kind of like the view you have now, what is there in the nebula is called the Orion Nebula,
right,
and the Orion Nebula cluster. But then if you zoom out quite a bit on the other, the large-scale image that showed the constellation, and I guess maybe we don't have at the ready a map of the dust or the molecular gas or anything like that, but there are other ways of viewing at other wavelengths than optical this area of the sky, and what you'll see is a big patch of dust. If this is viewed in maybe the WISE satellite or the IRAS satellite images where we're seeing the dust instead of the stars, you'll see a big swath of this area covered in dust and gas, and that is what's referred to as the Orion molecular clouds. And so it extends the Orion cluster, the trapezium, the Orion Nebula, the Orion cluster is the northern part of one of these clouds that extends way down to the south, and then there's another piece of the cloud that extends way up to the north, and it really does cover the full, nearly the full extent of the Orion constellation, almost all the way up to Betelgeuse, looking at it on the sky in the upper left, and all the way down to, let's see, is it Rigel or?
Rigel is bottom
Rigel's on the right.
I don't know the bottom left. It's the only one I don't know.
the other bright one down there. Yeah, that molecular cloud extends nearly all the way.
SEP, so what's the name? Yeah.
Yes. Okay.
So it really does take over the whole constellation.
So the whole constellation is covered on that side, which is the eastern side, is covered by this molecular gas. And then even across the belt, below the belt, there's another star called Sigma Ori, which is a small one. There's a cluster of young stars around that. I don't know if you're zooming in. Maybe we can find Sigma Ori. There's a cluster of young stars there, and then also way up in the north, Lambda Ori, which is kind of the head of Orion. Again, there's a big cluster of young stars there. And then also off to the west, there isn't any molecular gas, but there's a whole group of kind of high mass, not as high mass as young as are forming in the trapezium cluster, but there's a whole group of maybe 100 or so, also somewhat massive stars. They're a little bit older, more like 10 million years old instead of 1 million years old. So this whole constellation is filled with young stars, and as we've said, the most dramatic visible part to us is the Orion Nebula cluster. But if you look in the infrared and the dust and the molecular gas, this whole thing just lights up with young stars and young star clusters.
And if I can add, Lynn this morning was making a very interesting point that I realized, maybe I knew it, but you forget. But she reminded everybody that Orion, from the point of view of the constellation, just the drawing that you make in the sky of the warrior with the belt, the sword, everything you see when you draw exactly, basically everything is at the same distance. Is an amazing constellation. These are random drawings, but if you look at the Ursa Major or any other constellation, stars bright, faint, they're far away, one from the other. But in the case of Orion, they are more or less all at the same distance, about 400, 500 parsec, or 1,500 light years.
So they're all on basically the same plane?
It's pretty much everything is at the same distance, and everything is a monster. It's the closest giant star formation event that happened a few million years ago. And so we see like a distribution of ages. We understand some area formed like 10 million years, something like 5. Orion, the nebula, is the most recent, is 1 million years. Actually, there is star formation even right now in the nebula. But in general, it's like this I don't know, this event. Imagine the burst of stars in that place of the sky that happened nearly simultaneously.
Wow! So I didn't really know that about the constellation. So you're telling me that the stars in the constellation itself, the major stars that make up the constellation, are more or less the same distance away from us.
Yeah,
So that means that the stars that are being born this complex affects the stars like Betelgeuse and Rigel, and they're like affected by this, right?
They are affected, and actually, if you go with the right instruments, if you do, I don't know, for example, in the H alpha or in 100 micron, there are different tracers, but you can see spectacular pictures of giant rings, which are the remnants of supernovae that exploded very recently. We can still see the explosion, the material being blown away. And when you see these giant supernovae, normally they are associated with recent star formation because giant stars have a short life and tend to explode as supernovae, type 2 supernovae. So it's we see the entire collection of the entire phenomenology associated to star formation, large mass, small mass, is there in this place or in this part of the sky. So for astronomy is a fantastic region.
Let's ask our astrophotographer if has taken H-alpha images.
No, I've never. Well, I mean, my camera is modified, so it can get better H-alpha, but I don't have actual specific filters for it.
Yeah, the filter can be expensive.
It can be.
Yeah.
But it's, you can see in H-alpha images of this region, you can see what's called Barnard's Loop. It's a big loop off to the east side of the cluster, and then also around Lambda Ori to the north. Again, there's a big H-alpha piece that you just see in these fantastic images of the entire constellation.
An H-alpha filter is a good investment.
Definitely.
For Christmas.
One of these days soon, hopefully.
One of these days.
One of my other astronomers, this is from Paul Stewart. This is also an H-alpha plus with the rest of the spectrum here. But this is taken from New Zealand, actually. So
actually, let me just say real quick, Scott, Massimo, if this image doesn't appear big on your screen, you can just click on one of the little icons to get it bigger up on your screen, and you'll be able to get a better look. I don't know if you're trying to squint down at the thumbnail or not, so I just wanted to say that.
There's a little film strip on the bottom. If you click on whichever image you want to see, it'll make it large on your screen.
Do you see what I'm talking about, Massimo?
Yep.
I was trying to say that in case when you're looking at this Hangout, when Scott shows a picture and it's not big on your screen, just click on it and it'll make it big. Okay.
But I think don't know, Lynn, but with a glimpse, we can immediately, we navigate.
We know it. We know it.
We know the region well enough.
Well, not everybody knows, so I just wanted to make. I thought I saw you squinting at and trying to see it and looking at the thumbnail, so I just wanted to clear that up. So, okay.
We know the corner.
Okay, so this looks a lot different than the other one. I mean, in terms of colors and things like that. You said, tell me again what it was, Scott.
So this is taken by Paul Stewart, who's out of New Zealand, and these are 8 122nd. It's in LRGB, and also 8 shots of 300 seconds in hydrogen alpha. So he took these and stacked them on there, and as he likes to call himself, the correctly oriented astronomer, since he's upside down to us. But
constellation after all.
But so this is showing the difference in the different colors and the structures you're able to see when you are looking at these different wavelengths. So hydrogen alpha is something that's going to be more red to us than what we would see in the regular optical light that we see with our eyes all the time.
Yes.
Okay.
So, okay, Lynn, let me go back to something you said earlier on. You said that you were one of your areas of interest is stellar populations in the Orion Nebula. So, how many different kinds of stars are there? How are they distributed? And tell us a little bit about what you're finding when you look for these stellar populations.
Sure. So some of the interesting things about the stars in the Orion Nebula are, as we've said, there are these couple of massive stars that kind of create all the havoc that make the Orion Nebula beautiful. But there's an entire distribution of masses that go down all the way from these few tens, maybe 40, 45 solar masses for the most massive one, down to one solar mass, which is the mass of our sun, with more of these lower mass stars than there are higher mass stars, and then the distribution just keeps going down all the way down to about a tenth of a solar mass. So 10% of the mass of the sun is considered right around the limit for which stars are considered stars. That is, they burn hydrogen fuel in their center, right? Exactly. They burn hydrogen fuel in their center and are self-luminous and can live for billions of years. But the mass spectrum keeps going and into what's called the brown dwarf regime. So those are objects that are not massive enough so that the centers are hot enough and dense enough that they'll burn hydrogen and undergo fusion and become a main sequence star. So those brown dwarfs will just as they form like stars, but then they just continue to cool and contract and never stabilize themselves as hydrogen burning. And there are, there's as I said, a mass spectrum or distribution of masses where there are more low mass stars than high mass stars, and then somewhere probably above, seemingly above the brown dwarf limit, this mass spectrum turns over. And so there are brown dwarfs down there, but there are fewer of them than there are stars. This has been kind of a topic that's gone back and forth: is what's the true distribution? As I said earlier, when you shake up a molecular cloud and form stars, what falls out? And there's been some debate observationally, how we convert the things that we observe into something like a mass. Right? It's not very easy to measure the mass or the age for a star. We have techniques. We can measure its temperature, we can measure how bright it is, but we can't weigh it or carbon date it or something like that, like we do for more familiar objects here on Earth. So it's a bit of a challenge of going between converting what we observe into using our understanding of stellar evolution and theory to convert things into a mass. So for a time there was some kind of debate about how many brown dwarfs there were versus stars, and it's pretty clear in the Orion Nebula and in most other star-forming regions now that this mass spectrum turns over, and so there are fewer brown dwarfs than there are stars, but they're still there, and about 20% of all objects are probably brown dwarfs, and about 80% are stars.
Wow! And how are those mostly found in the infrared, the brown dwarfs?
Yes. Yeah.
You're laughing.
I'm laughing because you are talking about our next. I mean, Lynn and I are working on to exactly solve this problem using Hubble in the infrared.
Oh, okay. All right. So you're going to answer that question then, right? Are you going to be able to see them in the infrared?
Very soon we will have a precise census.
Okay.
Well,
okay, good. Good. I expect it. Okay.
At some point.
Soon in human time, hopefully
Soon
not
in human
astronomical time.
No, but there is an interesting, problem here which fascinates me. All these stars are actually only very few, and the largest one are burning hydrogen. We have these thousands of stars, and they are not burning hydrogen. They are so young that they are still preparing the hydrogen burning. They still need to shrink in size to raise their internal temperature. Eventually, they will burn hydrogen, but it will take 50,000 years, 100,000 years. The smaller stars will take a lot of time. Actually, the smaller will never reach that point, and these are what we call the brown dwarfs. So the interesting question is that even if there is something here that will happen in the far future, in hundreds of thousands of years, it is like if nature regulates itself so to have the majority of stars basically at this magic crossing point between burning or not burning. So there is something here that sort of regulates. Most of the stars are born just there, which is a fascinating point. How do they know what will happen in 100,000 years? So this is an open problem. We think that maybe other type of nuclear burning, like burning deuterium, may have something to do. But it's an interesting question. Why most of the stars form just at the mass where they will eventually burn hydrogen? It's a curiosity and an interesting problem.
Why would most of the stars that are born in this nebula
have the mass just at
that point where they start to burn? That's what most of the stars are.
Right. Most of the stars like to walk on the fine line, so to speak, which is interesting. Why they don't overdo on one side or the other, but stay on the line?
Okay, so here's where
they're like Johnny Cash then. They're like Johnny Cash, and they just walk the line.
Well, exactly.
Yeah. Okay.
Oh man. Okay. All right. Well,
that's what I'm here for.
That was it. That was the only one. Okay. So I guess I'm sorry, Massimo. I'm still trying to understand that statement because I thought Lynn said that there was a distribution of stars out there, and that the brown dwarfs were like 20%, right? And then there were. But you're saying the majority of stars that you're seeing in the Orion Nebula are those stars that are just massive enough for hydrogen to kick in, or fusion.
Exactly. But hydrogen to kick in the future. So there is something in the way the masses of the stars are produced, are distributed, that sort of regulates them at that point. And this is not only Orion; is a general relation. So this is an interesting problem that tells us that there is something there that we need to clearly understand.
Oh yeah, that's a fascinating idea. Thank you. I didn't realize that. I want to just take a moment here and ask you, Massimo, did you want to grab another person to come in, or do you want to just keep going? Because I've got some more questions if you want me.
I can grab. We have other guests here, so I can.
Let me give you an opportunity, and while I do that, Lynn, if you could just stay there, you can go grab somebody. And let me just thank Lynn for participating, and then you can go if you want to. But
or you can stay and hang out too. We like you.
Yeah, we'd like you to stay if you want to. So, did you give a talk already today, Lynn?
I did. I gave the opening talk this morning, the first one, and that's sort of fun because, well, as some of the conference organizers told me, I'm old enough now to give the history talk. So I've been working in this field for long enough that I have some connections to people, earlier generations of astronomers. I kind of have some corporate knowledge, so to speak, or some long-term knowledge, and so I was able to give what I thought was a pretty good overview of early studies. What I mentioned before, the just long time, hundreds of years fascination that humanity has had with the Orion Nebula region. From before we had telescopes, this just milky distribution that you referred to, that you can see with your plain eye, to the early telescope drawings, up through these various stages of technology. We've always gone back to Orion to test our equipment, to test our scientific theories about things we think we can conclude from studying other regions. What does Orion say? So we just use it as a test bed. And so my talk was the introduction to the conference. So I had a lot of territory to cover and to try to set up some of the other scientists who were going to be talking about the specific details of their research.
No pressure.
So it was a fun talk to prepare.
Yeah. Well, so over the years, over the millennia, I often say that we today in our current times, we are kind of in the golden age of astronomy. I mean, we live in a time when we are able to see so much of the universe in so many different wavelengths, and now we have space telescopes and we have ground-based telescopes and we have adaptive optics techniques for ground-based things, that we are getting unprecedented looks at the sky. And so one of the questions I have a favorite wavelength, so I wanted to ask you, what is your favorite wavelength to look at the Orion Nebula in?
My favorite wavelength, well, it's probably the mid-infrared and the far infrared, because it's just so different from what we can see or even just extrapolate with our eye. The processes are so different there, that it's just an entirely new look. So
I knew you were going to say the infrared. The infrared is everybody's favorite. It's my favorite too. I always say the future of astronomy is in the infrared. That's what I've always said.
It's true.
Anyway, Lynn, I want to thank you. You are more than welcome to stay, but I see Massimo has someone with him. Would you like to introduce him?
Sure, I'll scoot over.
All right.
And
thank you, Lynn. That was Lynn Hildebrandt from Caltech.
And I found Lee Hartman.
Hi, Lee.
Hi, how you doing, Lee?
Good.
Well, thank you for joining us. So I don't know if you know what you've been brought in on, but this is a hangout on air. We are broadcasting this on YouTube and on Google+, and we are basically just trying to capture some of the atmosphere that's going on with this workshop, and bring to the general public some of the things that you guys are learning, some of the talks that you're presenting, and kind of sort of get people going about the latest cutting-edge research that's going on with Orion. So why don't you introduce yourself? Tell us what you're working on. Tell us why you're here at this workshop, and what brings you with us.
Well, part of it actually was many years ago when Lynn was doing her thesis on the Orion Nebula cluster. I actually knew her, and we wrote a paper together. So that was actually the start of it. And more generally, I'm interested in how stars form and how clusters form. And the Orion is kind of the closest big cluster that we have to work with, and it's particularly interesting because it's not done forming. There's probably still going to be, well, we don't know, but it's certainly forming stars right at this instant. By instant, I mean the last 100,000 years. And, it could actually almost double in size by the time it's done, given the amount of gas that's lying around. So maybe we're seeing kind of like a cluster halfway or 2/3 of the way of being formed. So
you're saying when you say double in size, you mean then the stars that are currently there could double in size? It can double.
No, actually, what I mean is we have twice as many stars.
Twice as many stars that are existing now.
Yeah.
Okay. So you said you're interested in how stars form and how clusters form. Is there a difference? I mean, are they two different? Are the ideas involved in how stars form? It seems to me would be a little bit different than how a cluster would form, right?
Well. So I think that there's a unifying. I mean, personally, I think there's a unifying theme, which is gravity. I mean, gravity is ultimately responsible for for collecting stuff together, right? And that's what holds a star together.
Right.
And the star is a little different because it's got gas pressure. It's hot and whatever, that prevents it from collapsing down into a point. But probably, I think gravity, in the same way that gravity pulled the gas together to make the sun, let's say, that gravity would do the same thing to bring gas and stars together in a denser concentration, which is what we call a cluster.
So we were just talking about stellar populations a while ago, and Massimo made the point that, well, Lynn was telling us the range of densities and the range of stellar populations within the Nebula, that there were some, stars as big as 50 times the 50 solar masses, all the way down to brown dwarfs. And Massimo made an interesting point that most of the stars that they're finding are of the size that are just large enough for nuclear fusion to start. And so this would make this a very specific. If you think of it as a cluster, does that make the Orion cluster unique, or is it pretty much how all star clusters are? Because he was saying there's sort of not a bias, but a preference. Some process is involved to keep the sizes of these small stars the way they are, just large enough to start nuclear fusion.
Well, so the number of stars at each mass, if you look at it as a probability distribution, it looks pretty similar to other distributions that we see. So I think there's not a strong evidence that Orion is different in that respect than most other star-forming regions.
So if we could get a snapshot of an early
typical
complex
mass, as he says, which is.
Uh-oh.
Say again, we lost you.
Oh, I think you're back though.
Okay.
Okay, we must have. Oh, are you there?
Yeah.
Okay, sorry, we dropped you for just a second there, but I guess what I'd like to find out is, though, if we could look at another Orion complex, something similar to that, would that be you think that'd be a common occurrence then? What we're seeing in Orion, we just happen to be lucky because we can see it while it's still going on, all this star formation. But this is probably a pretty common way in which star clusters are being born, right, or being formed.
Well, we think so. I mean, there are lots more massive clusters. They're farther away, so they're harder to study. But to the extent that we can study them, they look, the peak mass, the mass most of the stars have, is pretty much like it is in Orion, as far as we can tell.
And we talk actually this distribution of mass is called initial mass function, and we usually attach the word universal. So there is at least in the general type of dependence, there is a strong indication for being on average the same. Maybe at the far end, in the very large masses, you may have situations where there is a variation, but it's always in the small number statistic. But when we study something very well, it's more or less the same.
Okay, well, we're getting close to the end of the time we have, but I want to get to some of the questions and comments that we have that we're seeing. But before I do, I got to ask you guys, what about planets? I mean, are you guys focusing primarily on star forming or just star formation and stellar populations, or is anybody looking at exoplanets? And I know there's protoplanetary disks in there, so presumably there's some planets that might have been formed in there as well. Is any comments on that?
That was one of the questions I was going to ask too.
Oh.
So.
I'm sorry, Michael.
I'm definitely in.
Way to ruin our guest's time here.
Oh, I did.
Man.
In fact, that was Michael's question, so you can answer him.
People are focusing in the exoplanet business on closer regions, right? So the nearest regions we have to look at planets forming in disks is basically regions that are about 3 times closer than Orion. So it's clear that planets must be forming, and there must be planets around the stars. But people are focusing on the nearer regions first, because they're easier to resolve the planets or see a structure in their disks that are making them. Or if you really want to, the only far away planet survey that there is Kepler, right? And that's kind of statistical. So those are the transits, and we can find very small planets that go in front of the star, right? But it's very hard to do any characterization because they're all far away, right? So what people are really focusing on for planets, for very, very young planets, let's say, are regions that are, at least 3 times closer or whatever, just because You know, it's hard enough as it is.
You have to consider that a pixel of the best Hubble camera is about the size of the solar system, 25
little perspective
astronomical units. So everything will be within a single pixel. And this is the one problem. The second problem is that to see a planet in the disk in that condition, you probably have to go in the infrared, because there are the disks that typically produce a lot of extinction. And when you go in the infrared, the problem with the resolution becomes even worse, because your natural shape of the point spread function becomes larger and larger. So you need larger facilities, you need interferometers, but then you need also photons with interferometers. And this is science that we need to leave something for our children to do.
Interferometry is something I know what it is, and I know Tony, but what do we mean by an interferometer? I think they're fascinating, they're wonderful, but what do you mean by an interferometer?
Oh, an interferometer is basically a big telescope where you cut out all the glass and you just keep the two extremes. Mm-hmm. But the two extremes must work like a single piece of a giant telescope. So all the difficulty, which means technically to keep them in phase. Otherwise, you just have two telescopes that get like two light collectors. But if you manage to keep them in phase, like imagine having a monster surface and you just take out all the glass, still the two pieces at the extreme give you an extremely sharp image. And this is basically the idea behind an interferometer.
Right, so like with arrays, like when you have arrays of telescopes, you have larger angular resolution, but you don't have the light gathering power as if it was one big mirror.
Correct, correct. And eventually, if you have an array so good and you start filling and filling and filling, you get the telescope, which is exactly. But when you start taking away, at some point you have an interferometer.
Right.
Okay, so Michael, I wanted to, I want to give you a chance. I stole one of your questions. Did you happen to have any others that you'd like to ask?
I was just kind of also curious about the trapezium. Is that like buried within the nebula, just kind of outside of it? Where exactly is its placement within that nebula?
So people have done a pretty good job of getting sort of like a 3D picture of the nebula. Okay, mm-hmm. And so if this is my eye here, I can't really do it very well, and it's clear that there's a lot of stuff behind. Okay, and then the nebula is sort of in front, mm-hmm. towards us, and people actually, in terms of like the star that's heating up that nebula the most, Theta 1c Ori, that you can actually estimate how far it is from the molecular gas, from the background stuff, in terms of how bright the stuff is that it's ionizing. And so I think it's about 0.3 of a parsec, or about that's 1 light year.
Yeah, I remember 0.1, but it's more or less the same, yeah.
Is it 0.1?
0.1
something?
So it's the number but
it's something like that, right? So it's just in terms of the size of the cluster, which is a parsec or more from the central mm-hmm. thing, it's just a fraction of that in front of this stuff. And there's a bunch of the cluster that must be behind it that's only visible in the infrared. So it's kind of, if you could kind of picture that, like the cluster is maybe, I don't know, 2/3 evaporate, the gas is coming 2/3 revealed by this evaporation of the gas, which is coming out towards us, and maybe another third or something.
Right,
like that.
And the wall is being pushed more and more with time. So
yeah. So basically, it's kind of eating up all the gas in the area that it's formed in.
Okay. Right. All the photons, all the heat coming from the star, kind of evaporates and has this stuff coming out, and it makes a big hole. In a big bubble.
And we see this wind coming toward us. If you take the right spectra, you see that the lines of the gas are blue shifted, which means coming toward us. It's a fascinating physical phenomenon.
So basically, it's kind of revealing itself to us.
We call it a champagne flow.
So if we wait another 500,000 years, we'll see the whole thing.
I can't wait.
A little space bubbly.
Yeah, 500,000 years. I'll be there. Okay, so anything else? You have any other questions, Michael?
No. Get to if you got any other questions out there.
Okay, well, it happens to be we're right out about the end of our time limit here. But Massimo, are we gonna do this again tomorrow?
As you wish. I mean.
Yes, I wish. Okay, guys.
Okay. So I second that wish.
yeah, so Massimo will grab a couple more people who is attending the workshop this week, and we will do this again tomorrow at the same time. So I hope that you will bring your Orion questions. Also tomorrow I'm going to bring a visualization that Frank Summers did of the Orion Nebula to sort of show people this sort of scientific rendering that he did of that. And we will also have other people that we can ask questions to. So I want to thank you, Lee, for joining us, taking time out of the workshop to just sort of give us a little insight into what you guys are doing out there. And Massimo, this was fun.
Yes,
thank you.
My pleasure.
All right.
Thank you to our guest.
Yes. Thank you
Bye.
very much.
Thank you very much.
Bye.
Michael, thank you for joining. It was a lot of fun having you here, and we will hopefully you're more than welcome to come back tomorrow if you'd like to. Hey, wait a minute!
What?
I forgot Ian. Was he?
He might be here tomorrow. He got hung up on a conference call, so he might be back tomorrow.
Okay, good. Okay,
Yeah.
good. So I was like, oh my gosh, I got so focused.
I got you
on
covered.
this.
Don't worry. I gave Mike the invite. I know you didn't give it to him.
So, yeah. Well, you have his email address. So we're talking about Dr. Ian O'Neill. He's he's from Discovery News. He was going to join us a little bit here too, but I guess he couldn't make it because of a conference call. So hopefully he'll make it next or tomorrow.
And
So
we have
if
some more
you
amateur
attend
astronomers as well.
event, you'll get an invite to the one I'm about to create for tomorrow. I didn't want to spam everybody with all these events, so I only created one. So I'm going to create that one next, and then you'll get an invite. It'll be the same time. We'll talk to 2 new people about the Orion Nebula, plus we'll have a few more graphics that we didn't have today. I want to thank Scott Lewis for knowthecosmos.com. Thank you very much for support. You were great you were a rock star with getting Stellarium up there. Thanks for doing that.
Absolutely.
And again, Michael, we look forward to seeing you on the virtual star party as well as more of your images. That was a stunning Orion image. It really was. Outstanding work. Oh, wait a minute. Before we go, we have a couple minutes. Can you give advice to anybody out there watching who is thinking about maybe getting into astrophotography? Okay, they're a beginner. They don't know what to do. They don't know. What advice would you give somebody who's just about to start out? Let's say they have a telescope. They've learned the night sky. They've looked at a few things, but now they want to take pictures. What advice would you give them?
A DSLR camera will be your best bet, and you can get some relatively cheap on eBay or Amazon. Adapters so they can hook up to your camera or to your telescope and basically just practice, see what works well on what you're trying to image.
Well, now wait a minute. I can't just use a Dobsonian on this, can I?
Oh, no. Well, a reflector telescope is what I use, but I throw it on I don't throw it. I gently place it on a equatorial mount.
Okay, but yes, so you almost always are going to need some way to track the sky because, as we all know, the Earth is turning, and so you've got to compensate for that motion.
And motor drives are definitely needed.
Yeah, so it is generally a pretty difficult thing to do, and I would highly recommend that you get really familiar with your telescope before you start it. You will almost definitely need a stable and sturdy mount, one that is not going to, as you walk by it on the ground, isn't going to shake. So you're looking at something pretty beefy. But most of the off-the-shelf, what are called go-to telescopes, where you just kind of type in, I want to see the Orion Nebula, and it goes, and it shows you the Orion Nebula. Those scopes tend to be pretty good for hanging an SLR off the back of. Is this your scope here?
Yeah, that's the telescope I use. That's an Omni XLT 150. It's basically a 6-inch mirror, and it's got the equatorial mount with aftermarket motor drives on it. And that's what I hook my camera up to.
All right.
Very
so that's nice. That's really nice. Good. Okay. So, and what would something like that cost?
Somewhere in the range of like $450 to $500 plus another $100 for the motor drives.
I'm sorry, but I got to tell you, that blows me away because back in the day, when I used to use Hyper 2415 film, and it was the kind of telescope you needed that was at least $5,000. Nowadays,
Were you using silver oxide for your film too, Tony?
Yeah, well, on glass plates, yeah.
Yeah.
Was,
okay.
Yeah, I gave the idea to Edwin Hubble. That's how old I am. All right, guys. Well, that really is all of our time. I want to thank you guys all for watching. This has been a lot of fun. We're going to try and do more of these throughout the year as the Space Telescope Science Institute holds more of these hangouts. I'm going to actually try to stream some of the talks in the future too, but that's an experiment. We do these things here at the Institute all year long, and I want to try and bring them out to you in some way or another. And here we've got all the experts on the Orion Nebula under one roof, and so we may as well start asking them questions.
Don't let them out.
I hope you guys will tune in tomorrow. I'm looking forward to doing this again. Also, later in the week, Scott and I are doing a hangout. I think you're going to this one, aren't you? The Comet Ison one?
Yep,
yeah,
I'll be there for Ison.
Sorry, I know you can't go to.
No, you can tell me to do things. That's fine. You know.
And on Thursday, the Hubble Space Telescope is going to be releasing its latest images of Comet Ison. They're processing that data now, and they're anticipating it'll be ready on Thursday. And we'll talk about the latest news for Comet Ison. They actually did the observations on October 8th. And they've been spending all this time doing the processing. We will announce it on Thursday. So we'll see you then. The event for that is already out there. So hopefully you'll click and say you're going.
I'll put that into the event page that we're in now. So link to the next event and the Comet Ison event. All the full-scale images that we showed today, I put that into the Google Plus event too. So if you're watching this on YouTube, go look for the Hubble Space Telescope on Google Plus, and you'll see our event with all the photos that are put in there and high quality. So for Mike and Paul's photos that we put out there, you'll be able to take a look at those in their full glory.
All right, awesome. Thanks you're a rock star for getting that done. I am such a crappy multitasker. I'm
actually an octopus, so I have 6 other hands doing
that's
everything.
Good. Yeah, well, I'm glad you were doing it. So, all right, Hubble huggers. I could have used a Hubble hangout earlier today, it turns out. Thank you all for watching, and as always, keep looking up.
Storming session on the line of the work that has been done in these years with the Hubble.
So is it Hubble centered then? I mean, you said you mentioned a bunch of instruments, which I should clarify what they were. The ACS, the Advanced Camera for Surveys. NICMOS was an older camera that was on Hubble. These are all cameras that you're talking about, imaging cameras, and now we have Wide Field Camera 3, what I guess they call it WISI 3 around here. So all of these observations, all of the workshops is based around observations done by Hubble?
No, there are of course data taken with many other observatories, telescopes, both from the ground and from space, X-rays, infrared, and especially tomorrow we will hear a lot about these other observations. On the other hand, let me say that Orion is a region especially good for the Hubble because it's sort of an exception in the field. Normally, when stars form, they are embedded and shrouded in the molecular cloud, in the neutral, dense, obscure material, dark clouds. But in the case of Orion, what happened is that there are giant stars that have blown out the material, so they have made possible for us to see through this cloud. So we see, we basically have a unique opportunity here, well, a rare opportunity to see star formation from an exceptional point of view. Basically, everything has been open to our view, so the Hubble can go through this cluster at optical wavelengths, which is the strength of the telescope. So it's sort of an ideal situation for us to see something extremely young, but already exposed to our view.
Awesome.
So this is why Hubble is central for Orion in particular.
So thank you, Massimo. That was wonderful. So that's the workshop. That's what's going on this week, and this is some of the reasons why they're having it. We're going to get into a little bit more of this later, but before I do, I need to let you guys know how you can interact with us. I forgot to mention that, as I always do. I just want to jump in an amateur perspective, as well as maybe if we have some time toward the end of it, we could talk a little bit about what's involved in astrophotography and how can a beginner get started? Because I think the Orion Nebula is probably one of the better targets. So
yeah, there's Mike's Orion right there, which is beautiful. Absolutely gorgeous.
Holy cow, that's amazing.
It's beautiful. Yep.
That's amazing.
And where are you out of, Mike?
I'm from Plattsburgh, New York, about 40 minutes south of Canada, near Lake Champlain.
Okay. So you have better skies than I do here in Los Angeles.
Yeah.
Just a little bit.
Or better than we have in Baltimore, I'm sure.
Yeah, most likely.
No, that's fantastic.
Okay, so Lynn, I'd like to get you in on this discussion a little bit. So, what were your reasons for attending the workshop, and can you tell us a little bit about what some of your interests are, your research interests?
Sure. Orion is just an iconic region, not only for amateurs and astrophotography and the general interest, but also for professional astronomers at a deep level. It has been looked at basically with every new technology we've had for centuries, and the talk I gave this morning at this conference outlined where we've gone basically from drawings in the early days of and early years of the telescope, right up through photographs, the first photograph that were taken, and on through the decades to our big space telescopes, both at optical wavelengths, the Hubble, infrared wavelengths, the Spitzer space telescope, X-rays with the Chandra space telescope, Herschel, which is a mid-infrared observatory, WISE, also a mid-infrared observatory, as well as a lot of ground-based data at long wavelengths from the millimeter, sub-millimeter.
And start talking about whatever it is the topic is whenever I do these hangouts. If you want to ask us questions, we would encourage you to do so. You can also leave comments on the YouTube channel, where this on Space Telescope or Hubble Site channel's YouTube channel, where I'm looking at the comments from where this video is being streamed. Also the event page, the Google Plus event page, and we are also monitoring Facebook and Twitter as well of the hashtag Hubble Hangouts. So we hope you will give us some questions and leave us some comments, and we'll look forward to getting to some of that stuff a little bit later on. And there's also a little square along the bottom that nobody knows who this guy is. His name is Michael. Hi, Michael.
Hello.
I don't know your last name.
My name's Mike Rector, and I am an amateur astrophotographer. I just set up my telescope with my digital camera and take long exposure pictures to just get nebula and galaxies and star clusters.
So I'm told that those who watch the virtual star parties on a regular basis probably know your name. Is that correct?
Yep, I've been on there a few times.
Yeah, it's one of our contest winners from last May. We had a photo contest of astrophotography, and Mike actually won with the Pleiades.
Yep.
A really great shot.
Yeah, your audio seems a little bit low to me, Scott.
I can turn up my gain. Yeah.
Yeah. Okay.
Is that a little better?
That's much better. Thank you.
I'm normally too loud, so I had to turn it down a little bit.
Tell me about it.
Stop yelling.
All right, so welcome, Michael. In your imaging efforts with your telescope, have you done much with the Orion Nebula?
Yes, I have. I actually sent a picture of Orion to Scott.
So Scott will get that up for us hopefully in a little bit. So, so that's cool. All right, well, welcome, and so hopefully you'll be able to provide some insight
on the Orion Nebula. We thought years ago that the Orion Nebula needed to be investigated in detail with the Hubble, and the main reason was at the time to study, to understand the stellar population of the cluster. You may not know, but the Orion Nebula, which is the spectacular object in the sky that everybody points the telescope in the first night after Christmas when you buy it, the Orion Nebula is actually host thousands of young stars, of young forming stars. So for astronomers, it's the prototype of star formation. If you want to understand how stars are formed and actually even how planets around stars form, the Orion Nebula is a critical place to go. So we pointed the Hubble. We had this monster program, more than 100 orbits, which means a lot of time. We observed the Orion Nebula with all the imagers on board of the Hubble. At the time was ACS with PIC2 and NICMOS, so in the optical, UV, in the infrared, really the full power of Hubble was spent there. This is the largest program ever dedicated to star formation. And we got the data. One of you may know the spectacular, big red picture of the Orion Nebula is one of the byproducts of this survey. took some year to put together the data, to clean up the catalog, to write a number of papers. Now everything is basically out, is public. We have released everything to the public. So the idea of the workshop is to bring here the leading experts, those that are working actively on Orion right now, to discuss the status of our understanding, what we have learned from these and other programs that are being carried out, that have been completed, and sort of plan the next steps to share ideas the way science works. We discuss and in these hours together, new plans. Each one comes with new ideas and new plans. So it's a brainstorming
now.
There we go.
Okay. Hello, everybody. My name is Tony Darnell. I work at the Space Telescope Science Institute. I'm the social media manager here. And this week at the Institute, we have something rather interesting. We're trying kind of a bit of an experiment here because today, tomorrow, and Wednesday, we're having a workshop on the Orion Nebula. And this workshop is designed to kind of present some of the things about the Orion Nebula. What do we know about it? What are some long-standing issues that we're maybe finding more things out about? What are the what's the latest research? What's the new research out there regarding this very famous nebula? If you don't know what the Orion Nebula is, then not only are you in the right place, you're going to find out what that is, but also the cutting-edge research that's being done here. So with me today is my co-host. He's always out here sharing these hangouts with me. Is Scott Lewis from Know the Cosmos. Hi, Scott.
How's it going, Tony? I prefer cohort instead of co-host.
All right,
we get up to some trouble sometimes.
Cohort, yeah. So all right. So cohort. Now I was going to call this a Hubble Hangout, but because this particular topic is more about research done by a lot of other things besides Hubble, kind of, I didn't bring it up this time. But usually we call these under the moniker of Hubble Hangouts. And so with us today are some astronomers attending the workshop, Dr. Massimo Roberto from the Space Telescope Science Institute and Lynn Hildebrandt from Caltech. Hi, guys.
Hello.
Hi.
So Massimo, why don't you start us off by telling us a little bit about this workshop? What are you hoping to accomplish, and why are we doing these kinds of things?
So basically, the story of the workshop starts almost 8 years ago when we got approved the Hubble Treasury program.